Hello, welcome back. The title of this lesson is called Uniform Circular Motion. First thing we're going to do here at the beginning is I'm going to write down a simple diagram and an equation or an expression that tells you how to calculate the acceleration that comes about due to uniform circular motion. The second thing is we're going to solve a problem so you get some practice with it. And the third thing is, if you stick with me, we're going to derive by doing the vector math necessary to prove to you, mathematically prove to you what the equation for acceleration for uniform circular motion is. Now, before we get started, I kind of gave the punchline away a little bit, but pretend I didn't say that. So here is what we call uniform circular motion. Here I have, in this case, it's just a chord. That's a distance r away from a center rotating point, and you can see that it's spinning around in a circle. The amount of situations where we have uniform circular motion is mind-boggling. We use it when we talk about chemistry and atoms. We actually use it when we talk about planets and galaxies, galactic motion. We use it when we talk about mechanics, cars driving down the road and the wheels are spinning. We use it when we talk about almost any kind of mechanical system that rotates. I mean, anything from a mechanical engine, anything that has a circular motion, we're going to be using the ideas in this lesson, right? So it's very, very broad. And it's probably the first time in physics for a lot of people where the result that we get, it goes a little bit against what you might think originally. Now, and that's something that you got to get used to, because the more you learn, the more you realize that the more you don't really know, right? So here's going to be your first situation where a lot of people will think, well, that doesn't really quite make a lot of sense. So my goal here is to make it make sense. So here we have uniform circular motion. What I mean by that is the speed at which the end here is going around and around the center part is an unchanging speed. So you might say the tip of this cord is going round and around at a uniform speed of, I don't know, 100 centimeters per second, or whatever it is, half a meter per second, whatever it ends up being. And that means if I were to freeze time, of course, it's moving this direction. Instantaneously, the velocity is going to be whatever it is. And then a nanosecond later, when it's over here, then it's going the exact same speed. The only real difference is it's the same speed, but the direction is always changing because I'm going around and around in a circle the entire time. Now, my question to you is, if this thing is going around and around at a fixed constant speed, is there any acceleration happening in this situation at all? And I think most people, if I didn't give you the punchline ahead of time, would say no, there's no acceleration. Because we talk about what acceleration means in the beginning part of physics. We say that when we have a changing velocity, that is what we call acceleration. You're sitting in a car, you're at a red light, you floor it, you get pushed back in your seat, that is what acceleration is. And we associate it with when your speed is changing, right? And that is true. It does occur when your velocity is changing. Now, in this case, I'm telling you that the speed of this tip of this circular motion here is going around and around. We're not speeding up or slowing down. We're just going a constant motion all the way around. So is there any acceleration happening here? And the answer is yes. There is definitely 100% acceleration happening in this situation. And you might say, well, how is there acceleration happening? You just told me the tip of the thing was going around and around at a constant speed. And if acceleration measures how the speed is changing, how can you have any kind of acceleration? Well, that's because when we talk about the idea of acceleration, it's the change in velocity when we divide by delta t, the change in velocity divided by the time elapsed, right? But here's the thing, and here's the punchline. We're going to get into a lot more here in just a minute. But the change in velocity necessary when we're talking about vectors, which velocity is a vector, you can make a change in velocity by increasing or decreasing your speed. That is true, but you can also change your velocity just by changing the direction. If you think about it for a minute, if I were to freeze time, then at this moment in time right here, my velocity vector is pointed to the right. It's a magnitude, a length, and a direction pointed this way. But a little bit later, when I've rotated, the magnitude of the velocity is the same because the speed has not changed, but the direction of the arrowhead has changed. And as I go down to the bottom and I'm making my way back up to the top again, my speed is always the same, but the vector arrow direction is always changing. And what I'm telling you here is the punchline is when you have a change in velocity, it can be in a vector velocity. Yes, the speed is not changing, but the direction is changing. And a direction changing counts when you start talking about, do I have a change in velocity or not? Because a velocity going this way and a velocity going this way are different because they're pointed in a different direction. So yes, you can have a constant speed where you're not speeding up or slowing down, but because the direction of motion is always changing, then you have a changing velocity. And when you have a changing velocity, you have a changing acceleration, or you have an acceleration, I should say. So let's draw some pictures. It's going to become a lot more clear, and I'm going to bring it down to everyday life and everyday experience for you as well. All right, so let's say that we have a center. Now, I'm not going to be able to draw perfect circles, so just forget about that. I'm going to do the best that I can, so don't hate me too much if I can't draw a perfect circle. But here we have what I'm going to attempt to draw is a circle. Now, is it going to be a perfect circle? No, it's not going to be a perfect circle. I just told you it's not going to be a perfect circle, but that's the best circle I can draw freehand. This is me holding it in the center, and then I'm flipping this thing around. You can think of this being a wheel that's turned. You can think of anything that has a circular motion associated with it, okay? And what I'm basically saying is that at this point right here, if I could do a snapshot in time and say, what is the velocity vector, because the thing is going this way, what is the velocity vector at this moment in time? Well, it has some length and it has some direction. And we're going to call this velocity like this. And the velocity vector is always, remember, tangent to the path. And we'll talk about that a lot more when we get to calculus, but we've already learned, even in physics, that the velocity vector is always tangent, means just touching in one place the path of the motion. That's why it comes off like this. This means that if I were to cut the cord, the particle would sail in a straight direction like this. But of course, I'm holding it with a cord and I'm kind of flinging it around, and so the path is always changing and going down like this, okay? So let's say, what do we have in this position right here? Well, the velocity is now pointed in a different direction, but the length of the arrow is the same, or I'm trying to draw it the same. What about over here? Where is the velocity vector? Well, it's tangent to the path right here. Same length, different direction. Where is it right here? You see the pattern. Same length, different direction, velocity vector. Maybe that's a little too short, but trying to make them all the same. Where is it right here? Well, trying to make the same exact length, and I'll do the same thing right over here. All right. So when you ask yourself, we ask ourselves, what is the definition of acceleration? The definition of acceleration that we used in the past is we said that it was the change in the velocity divided by the change in the time, or how long it took. Now, in this case, we're not talking about one-dimensional motion anymore. You know, in the past, we talked about one-dimensional motion, only along x, right? But we're not doing that. This is two-dimensional motion now. So it's a vector that has direction as well. Whereas in one dimension, I mean, we could only go this way. So there was really no direction other than plus or minus x. So when we say a change in velocity by time, this change in velocity can happen two different ways. Way number one that you can have a velocity change is literally to speed up. Like if you're driving around the circle, you kind of speed up and put more gas into the engine. But another way to get a change in velocity is to hold your speed constant, but just change directions. Because this velocity vector is completely different than this velocity vector. Yes, the length is the same, and that's because the speed is the same, but this one is pointed there, and this one is pointed there. And remember, a vector has magnitude, which means strength or how big the number is, and it also has direction. The direction is equal part of the vector quantity. And that's why we learn vectors in physics, because you can't understand this without understanding vectors, right? Because you think that if you don't accelerate its speed, then there's no acceleration, but that's not true. Because in vector land, you have magnitude, how many meters per second you're going, and you have direction, how are you pointed? And if you're not changing your speed, if your direction is changing, then the vector is different. And if the vector is different, it has changed. So what is the change in this velocity with respect to time? That should yield some sort of acceleration. We're going to call it a centripetal acceleration. Centripetal is a word that means center seeking. So let's write down what that acceleration looks like. When you look at this point in time, when the velocity was going this way, the centripetal acceleration, or the radial acceleration, it points towards the center of the circle. I'll put a little dotted line to kind of remind you that it's pointed to the center of the circle. And right here, it should be the same exact length in terms of acceleration, but pointed to the center of the circle there. Here, it should have the same exact length, like this, pointed to the center here, same exact length. Here, pointed to the center of the circle, same exact length. And pointed to the center of the circle right here, same exact length. So, Do you have an acceleration? Absolutely. At this point in time, this thing is accelerated, pointed toward the center of the circle. Here, the acceleration is pointed toward the center of the circle. Here, the acceleration is pointed to the center of the circle. Here, the acceleration is pointed to the center of the circle all the way around. So when you have uniform circular motion, which means constant speed, no speeding up or slowing down, we're just changing directions in a circle, the acceleration vector always points to the center. Right? And we're going to calculate the strength of that acceleration in just a minute, but I want to focus more on the direction because that's what's so weird about it. You don't think there should be an acceleration here because you think that if it's not speeding up, there should be no acceleration at all. But now, not only am I telling you that there is an acceleration, but the acceleration is not even pointed in the same direction as the velocity at all. It looks completely nonsensical. How can the acceleration be pointed in a totally different way than the velocity? So let me clue you in on something that we're going to get into a lot more later on, but I'm going to show you earlier because it'll make it a lot easier to understand. In general, the acceleration can point in a totally different direction from the velocity because of the following thing. In a later lesson in physics, very soon actually, we're going to start to talk about forces. And a force is when you push on something or pull on something. It could be a force because I'm literally pulling on it or pushing it. The force could be because of a spring that's pulling or pushing on something. The force could be a rocket engine. The force could be gravity. The force could be the electric attraction or repulsion between an electron or a proton or whatever. Forces are all around us. I think you have an idea what a force is. I can push on this board with a force. Now, what we're going to learn later is that forces and accelerations, they always go hand in hand. I haven't taught you that yet because we don't get to forces until the next chapter. Maybe it's the chapter after that. But basically, anytime you see an acceleration in real life, there's always a force involved. Think about it in your car. If you're accelerating, how do you do it? You have to spin the tires more, which creates a force. And that comes from the engine, right? From the chemical reaction in the engine, from the burning, right? If I'm in a rocket ship, how do I make an acceleration? Because remember, if I'm just turn off the engines, the ship is going to fly forever in the same direction. That's another law that we're going to learn, is that things go in the same direction unless you do something to change that direction. If I cut the string, the rock or whatever it is going to fly off in this direction. Or if I cut it here, it's going to go in this direction. So how does this make sense in the context of our little demo right here? Well, I'm telling you that anytime you see an acceleration in real life, anytime, there's always a force associated with it. Where is the force in this problem? Well, the force is my fingers. The force is literally pulling. If you could freeze time and look at it, when it's at the top, I'm pulling down. When it's over on the side, I'm pulling slightly that way. When it's on the bottom, I'm pulling up. And that motion is a little circular motion that my hand is doing, but I'm always pulling toward the center. And the center pulling that I'm doing all the way around is lined up with the acceleration, which is always pointed to the center. So we're going to learn a lot more about forces later, but for right now, anytime you see an acceleration vector arrow, you need to imagine a force pulling in that direction because forces and accelerations go together. Now let me ask you this. How does that explain this motion? Well, things want to go in a straight line, always, forever, unless they're acted upon by some force, right? If I just throw something, it's going to go forever and ever and ever unless gravity or something else changes its course. In the case of this spinning thing, it wants to go in a straight line direction, for instance, like this, or like this, or like this. But when I'm pulling on the thing, when I'm pulled down, it causes the path to curve till I get to this point. But when I get to this point, I'm pulling inward. It wants to go straight, but I'm pulling in and it curves the path more to get to here. But when it's here, I'm pulling this way, which curves it to here. And I'm pulling up, which curves it. Pulling up, curves it like this. So at every point around the circle, I am literally pulling it. And the pulling, the force, is changing the path. And that changing path creates a circular motion. That is why an acceleration makes sense to be pointed toward the center. Because accelerations, they never happen without forces. We're going to learn about Newton's law. It's literally force equals mass times acceleration. The force is always in the same direction as the acceleration. So there has to be an acceleration like this because in order to make a circular motion, I have to pull, right? If you think about the planets orbiting the sun, now the orbits of the planets are not exact circles, but they're pretty close. Where is the force coming from to hold the planet in orbit? It's the gravitational force. When the planet moves over here, gravity's pulling in. When the planet's over here, gravity's pulling in. When the planet's somewhere else over here, gravity is pulling in. It's always pulling in, and that pulling in is changing the path. So you see, When you're in a one-dimensional car and you give force, you accelerate, you increase the velocity. In this case, the force is not increasing the speed, the force is just changing the direction, and the speed is unchanged. So that's why this acceleration makes sense, because it is related to a force which is necessary to curve the path. So forces can either speed things up or slow things down, which would give you an acceleration, or forces can just change the path of whatever it is you're studying. A changing path means a change in velocity, which also means an acceleration. So you can have accelerations totally different than the direction of your velocity, because those accelerations, which are not lined up with the velocity, are just simply going to change the path into a new path in a new direction. Now this type of acceleration we're going to call centripetal acceleration. But before we write that down, we're going to say that the vector A points to the center of the path. It points toward the center of the path. And what is the equation for this thing? The equation is A, we're going to put RAD, that means radial, it's pointed inward, and it's equal to V squared over R. R is the distance from the center, the radius of the circle, and V is the velocity. It's just the tangential velocity all the way around. Now notice that it's V squared over R. It's not just V over R. But if you know how fast something is traveling around a circle, around the periphery of a circle, and you know the radius of the circle, then you immediately calculate the acceleration that's happening there, and you automatically know that the acceleration is pointed toward the center of the circle always, no matter where on the circle you are. And this equation is telling you to calculate its, or to allow you to calculate its magnitude. And the direction is always pointed toward the center. Now we're going to use this to solve a problem, but before we do it, I want to talk about this equation a little bit more. Because a lot of students, including me, when I learned this, I was like, well, why is the acceleration V squared over R? Why isn't it just V over R? Why isn't it 2V over R? Why is it? We're going to derive this equation in just a minute. But in order to talk about it a little more intelligently, let's take two situations. Let's take a big circle like this, and let's take a small circle right next door with a smaller radius. And let's say that here I have exactly the same velocity, and I have exactly the same velocity right here. So what we're basically saying is if this distance here, how do I want to draw this here? Let's say this is 1/2 of the radius, and this is one radius, and this is 1/2 of the radius. So basically this circle is half the diameter of this one, basically. What we're basically saying is if the velocities are the same, you're going to put the same number in the top, but you're going to divide by R. But if R is smaller, then you're dividing by a smaller number, and the acceleration gets bigger. So my question to you is, if I make the circle smaller, why does it make sense for the acceleration to get bigger with the same velocity, right? Well, if the velocity is the same, then since this is a smaller path, it's going to actually complete a circle much faster than this one, right? Because the speed is the same, 5 meters per second or whatever, but the path is smaller around this circle, so it's going to make more circuits. And it's going to be changing direction a lot faster, because if it's making a circle faster, remember, the change in direction here is what's causing the acceleration, or what's related to the acceleration. And if it's going around the circle many more times, in more circuits per second, or whatever you want to call it, more revolutions per second, then the velocity vector is changing much faster, and that means the acceleration must be higher. So when the radius goes down, acceleration goes up. So we can say that when the radius goes down, the acceleration goes up. Right? Now let's talk about something else related to that. Let's say a different situation. Let's have two circles of the same exact size. So same exact, I didn't draw that second one great, but it's the same radius. So we'll put, here's a radius here, and right here is a radius right here. And let's change the velocity in these guys. So let's say this one has a velocity v, and this one has a velocity of 2 times v. So it's literally, I guess that's way too big, but something like this, 2 times v. Something larger, okay? Or you could say v1 and v2, whatever. So what's going to happen here is, according to this equation, if the radii are the same, this number is the same, but if we increase the velocity, what's going to happen? The acceleration is going to get way faster. But it's not just going to get faster, it's not going to be double, because the velocity is going to be double. You're going to have a 2 times v that goes in here. So what you're going to have is 2v squared over r. And when you do this, it's going to be 2 times 2 is going to be 4v squared over r, because the exponent applies to everything on the inside. So you see, if you actually double the speed of the thing, it doesn't just get double the acceleration, it gets 4 times the acceleration. Why does it make sense for, if you just double the speed, for the acceleration to double so much? Well, you know that you can increase your acceleration is positive, or you get an increased acceleration if you speed up in a car even. So if I double the speed, I'm going to pick up acceleration just because I increase the speed twofold, right? But after I have increased my speed to double the speed, I'm going to be going much faster around the circle than this one. And so it's 2 effects there. One of them is going to be a doubling of acceleration just because I increase my speed. And the other one is going to be the direction vector as I go around it's going to be changing faster because I'm now making circuits of this thing much faster. So it's going to be rotating faster than this one, and that's going to also increase my acceleration. So both effects together mean that when you double the speed, you don't just double the acceleration, you 4x the acceleration. Some of that is increased just because of the speed I'm increasing, and some of that is increased because of the increased speed, the direction around the circle is also changing. Remember, the acceleration is the change in velocity over time, but the change in velocity can happen just by speeding up, and also a change in velocity can happen simply by changing directions of the velocity vector. All right, so let me check my notes, make sure I wrote everything down. This is called, I think the one thing I didn't call, this is called centripetal acceleration. The word centripetal comes from Latin, which means center seeking. So center seeking literally is centripetal, and it's literally an acceleration pointed toward the center of the circle. I said forces causes acceleration, so forces can cause you to speed up or slow down, that accelerates, but forces can change the direction of things, which also can cause you to accelerate. And if you imagine this being a force, then it makes sense that the acceleration is pointing toward the center of the circle. I talked about that. Okay, so I think we're ready to solve our first problem, and then after that we're going to derive and make sure we understand why it makes sense that this is the actual equation. So stick around for the derivation. The problem says, some greyhounds can run 45-meter diameter turn at an amazing speed of 15.0 meters per second. What is the acceleration that the greyhound, undergoes as it rounds the turn? So we're literally just doing a straight calculation of the acceleration. We're basically saying that there's some kind of circular path here, right? Some kind of turn, right? And we're saying that the diameter here of this circular turn is 45.0 meters. And it says that it can do this turn with a velocity of 15.0 meters per second. And it's just a straight question, calculate the acceleration. Right? Well, the acceleration, which is pointing toward the center of the circle, assuming the velocity is constant as we make the turn, is v squared over r. So we say that the acceleration is v squared over r. This is the magnitude, the amount of it, right? The acceleration we have, it's just 15. So 15.0, we're going to square that. Now we have to put it over the radius. But the radius is going to be 45 divided by 2 because we were given the diameter in the problem here. So the radius works out to be 22.5 meters when you take the 45 divided by 2. And then you put 22.5 right here, and you have meters. You're going to get on the top 225.0 when you square the 15, and then you have the 22.5 on the bottom, and so the acceleration is 10 meters per second squared. 10 meters per second squared. And what direction is that acceleration? Towards center. For uniform circular motion, it's always toward the center. In other words, if the greyhound is here, then the acceleration is not going this way. The acceleration has to be pointed to the center of the circle, because the acceleration amounts to like a force, and that's kind of turning him and causing him to make a turn, a change in the direction of the velocity, in other words. And by the way, where's that force coming from? It's because as he's running, he's pushing on the ground. And that's what's turning you. When you run or when you turn like that, when you're running, you're pushing on the ground. That's a force that you're exerting that's doing that turning. Now, if you're curious about the units, what you have on the top is meters per second, and that's squared. That's v squared over r, which is meters. So on the top, you're going to get meters squared per second squared. On the bottom, you're going to get meters. or you can do meters over 1, right? Which means meters squared per second squared, and you change this to multiplication, flip the second fraction over, 1 over meters, and then you're going to get a cancellation right here, and so you're going to get meters on the top and second squares on the bottom. This is a unit of acceleration. So when you do v squared over r like that, the units you get out of it should be acceleration, meters per second squared, as you would expect. So literally a straight calculation, put the tangential velocity, this has to be the tangential velocity, tangential to the circular path, square it, divide by the radius, not the diameter, the radius, and then you're going to get that acceleration pointed to the center. Now for the grand finale. I didn't want to front load it, but now we need to talk. We need to talk a little bit, because I don't want you to just trust me. I want you to understand how this equation comes about. Our goal is to prove to ourselves that when we draw the situation and we calculate this, we know the acceleration is the change in velocity vector divided by the change in time. Out of that comes v squared over r. That's what we want to prove. You don't really have to know this on a day-to-day basis, but it's not hard to understand, and I think it will enlighten you, and it could be asked on an exam too. You never know. All right, now what we know, where we're trying to go, is we want to calculate. We're going to start by calculating the average acceleration between 2 points of time, and then we're going to take the limit and shrink the time down, as we always do, and we're going to end up finding that the instantaneous acceleration is v squared over r. But we got to start somewhere. We know that the average acceleration between any 2 points in time is the change in the velocity divided by the time interval. And this means some final velocity v2 minus some final velocity v1. These are vectors, and then the time interval is t2 minus t1. So all we have to do is figure out 2 points on the circle, take the final velocity as a vector, subtract the initial velocity as a vector, and then we divide by the time interval. And that is going to give us the acceleration. And out of that should pop v squared over r. So let's go ahead and write down what the circle actually looks like. Now, my drawings are not going to be great. They're not going to be wonderful, so just try to be a little patient with me, right? So what we have here is a semicircle right here. This is obviously a little bit bulging. It's not exactly right, but you get the idea, okay? And we're going to have 2 points on this circle. We're going to have one point, we're going to call it A, and we're going to have another point over here called B. And again, this is not exactly a circular shape, but you get the idea. Now, what is the velocity at point A, the tangential velocity? You got to remember, this is uniform circular motion. It's not speeding up or slowing down. So the velocity is tangent to the direction. So we're going to call this V1 or VA if you want to. And this one is going to be in a slightly different direction, V2 or VB. Notice the lengths of the arrows are the same because I'm not speeding up. It's just the direction of the velocity is different. So this is a velocity as a magnitude and direction, and that one has a magnitude and direction there. So now I need to draw some additional decorations on this drawing here. All right. And what I'm going to do is from point A, we're going to draw like a dotted line that comes in to the center, and we're going to make a little pizza wedge like this to the center as well. Now this is the radius of the circle, and it's the same for both sides because the radius is the same going to the center, right? And then there's some angle here, and this angle I'm going to call it delta theta. Or sorry, not theta. This is the Greek letter phi, right? So, but it doesn't matter what. You could use alpha, beta, whatever. I don't care. But it had some measurement of the angle there. Now, we're going to start with these points far away. We're going to calculate this, but then we're going to let the points get closer and closer and closer to time. So this angle is going to get smaller, but the radii are going to stay the same because the circle doesn't change. The velocities are going to stay the same in magnitude, but they're going to get closer together. So you can imagine that this is going to start rotating in like this until the points A and B get basically right on top of each other when we take the limit, okay? So what is the remaining thing we need to add here? What is the distance between A and B? The straight line distance, I'm going to draw it with a straight line like this. And this is called delta S, right? S is going to be the distance from A to B. Now, right now, it's a straight line distance, so it's a little different than the distance through the circle. The circle's curved. But as we bring A and B together, this straight line distance is going to get closer and closer and closer to the arc distance. You see, the arc is a little different than the straight line distance, but as we take the limit, and this is why we take the limit, right? As we take the limit, the straight line distance between A and B is going to get increasingly close to the arc distance until when they're right on top of each other, delta S, the distance here, straight line distance, is going to approximate the arc distance pretty much exactly as we take the limit and make it smaller and smaller. All right, so now what we have to do is we have to draw a second circle with some additional stuff. We have to actually perform this vector subtraction, right? So let's kind of go over here and let's draw the center of the circle again. And then we'll try to, this is where I'm going to really struggle, because to make it really good, you have to make the circles like the same size and all that, and you can just tell that it's not. But you get the idea. I guess I can just cheat a little bit, put the center over there, like this. So what we have to do to calculate the acceleration is we want to take v2 minus v1. So v2 is over here at b, so I'm just going to try my best to put b in the same location. All right, and I'm going to put v2 something like this. I'm trying to, see, it's already wrong, but you get the idea. Let me go ahead and move it a little bit more tangential, like that. That's pretty close. It's not exact, but you get the idea. This is this right here. So this is v2. So if we want to subtract v1, what we have to do is we have to flip around the direction of v1, because that makes it negative v1, and then we can put it head to tail. So if we take this and flip it around and then move it over here, it's going to be pointed like this. This is negative v1. So we want to take v2 minus v1. The way we do it is we take v1 and we make it negative, and then we add it to v2. That's the same thing as v2 minus v1. If you add these two together, it's the same as v2 minus the vector v1. So what do you get? I'm going to draw this like this. It's going to be something like this. And notice that this arrow is pointed not exactly to the center of the circle, but it's pointed kind of toward the center of the circle. Now what's going to happen is as we bring these closer together, these arrows are going to get shorter and shorter, and this triangle is going to get shorter and shorter, and this arrow is going to start to point exactly into the center of the circle. So it's not pointed to the center now because the points that we have along the circle are pretty far. But as we bring them together, the arrow is going to point, I think you can convince yourself as we bring it together, these arrows get shorter, everything gets shorter, and then it starts to point more and more towards the center of the circle. So what we have right here is v2 vector minus v1 vector, like this. And let's see, what else do we want to put here? Right. So I think I can erase the rest of the circle. I don't think I need the bottom of the circle right here. That suffices here. And we can kind of draw the punch line. We can say, all right, what we'll do is we'll draw the circle one more time over here. We'll kind of make it a little smaller. And then we basically say that over here at some point on the edge of the circle, when we have, you know, a velocity vector like this, call it v, and it doesn't change as we go around the circle, the direction changes, but not the actual magnitude, then the acceleration points directly towards the center. As we're here, it's starting to point toward the center. As we bring it closer in together, it's going to get closer and closer and pointed exactly to the center. Now, how do we get from this to the actual equation v squared over r? So what we have to do is realize that these two triangles are actually similar triangles. Similar triangles. This triangle and this triangle, these are similar triangles. And you can prove that to yourself with geometry, but for now, we're just going to basically say that this angle right here is delta phi. This angle is the same angle as the one here. The angles are the same. The length of this is different than the length of this, but everything's proportional. In other words, this one is bigger and this one is smaller. This one is bigger and this one is smaller. The angle in the center is exactly the same. So because the angle is the same, all of the, and because of the geometry of what we've done, we basically took the lengths of these and made them and used the vector lengths over here. And so because of that, we know, or you can, I should say, prove to yourself that this angle is the same as this. If you bring these closer together and make this angle smaller and smaller, then what's going to happen is these are going to get smaller and this is going to get smaller and the angle's going to close in eventually when they're right on top of each other. So the angle's going to get smaller and smaller just like this. So you have to accept that these triangles are similar, which means that the sides are proportional to each other. Okay, so what we can do is we can say this side, the green side here, if we take the magnitude of it, and that's the magnitude of delta V, magnitude just means the length, right? And then divide that by one of the other sides, the magnitude of V1. This is negative V1, but its magnitude would just be V1, right? So if we take the magnitude of this vector, of the resultant vector, and divide it by the length of one of these other sides of the triangle, that's going to be exactly the same because this corresponds to this side, delta S, compared to R. All we're saying is the ratio between this side of the triangle and this side of the triangle is the same as the ratio of this side of the triangle to this side of the triangle. Why? because they're similar triangles. And they're similar triangles because the second triangle came from basically the vector lengths that where we drew in the first triangle right here. And the angle and so on comes from the geometry there. So where we're going is we want to take delta V and divide by delta T. So we're going to solve for this guy. So we're going to say the magnitude of the change in the velocity is going to be delta S divided by R multiplied by V1. So all we did was multiply by V1 and bring it over here. So now we have to bring it home, and we have to say that basically what we want to calculate is the average acceleration, which is delta V divided by delta T, delta V as a vector divided by delta T. But now we know what the magnitude of delta V is. I guess I could put absolute value around there. So the amount of acceleration we have is the magnitude of the change in the velocity vector divided by delta T. And we have this here, which is delta S over R times V1. And when you divide by delta T, you're just going to slap a delta T down here. You're just dividing by this, and so you divide by this on the other side. So what we did is we used the graphics and the similarity of the triangles to tell us this relationship to find what delta V is, absolute value-wise. And since we know delta V divided by the time is the acceleration, we just take that and we divide by the time. And this is the average acceleration. And now what we want to do is we want to take the limit. We want to say that now we're going to change it from an average acceleration to an instantaneous acceleration, which is the limit as delta T approaches 0 of all of this stuff, which is delta S over R times V1 over delta T. Now what I'm going to do next is I'm going to take the limit, or I'm going to rewrite what I have. Delta T goes to 0. I'm going to put these quantities on top next to each other, and I'm going to take the other two, V1 over R, I'm going to put them together, and then delta S over delta T, I'm going to put them together. This is the same thing. These are multiplied together, and these are multiplied together. I'm just putting the two terms with the delta right next to each other. Now when I change time, and make it get smaller and smaller. Of course, this changes, and the delta S, which is the distance between the points, changes, but the radius doesn't change, and the velocity, V1, doesn't change. So I can actually pull this outside the limit because as time changes, these don't change at all. So what I can say is that's the same thing as V1 over R times the limit as delta T goes to 0 of delta S over delta T. All right? And so my question to you is, what is the limit of delta S, delta T? Delta S is how fast this distance is changing, and delta T is the time. How fast distance is changing divided by the time. Distance over time, distance over time. What is distance over time? This, how fast this thing is changing with respect to time, that's just going to be how fast the particle is moving, V1. So you could call it V1 or V2, but when you look at delta S, the change in S divided by the time, then that is basically just going to be V1. So let me go on the next board and write down where we ended up. We basically said that the acceleration was going to be equal to V1 over R times the limit as delta T goes to 0 of delta S over delta T. But we just said that when we take the limit of delta S over delta T, as everything gets small, that's just the speed of the particle. So what this means is that A is V1 over R, and we could just call this entire thing V1. How S changes, the distance between these points divided by the time is just the speed of the particle. So this is V1 here. And what do you get here? You get V1 squared over R. But then you realize that's basically what we're looking for, but V1 squared, the velocity is the same all the way around the circle. So we don't need to keep a track of V1 and V2 anymore. We can just say A is equal to V squared over R at any point along the circle. Okay, so you can say this is sometimes you see radial acceleration or centripetal acceleration, V squared over R. So just to bring it home from the top, just to make sure we're totally clear, because it can get lost, believe me. Even I get lost sometimes, often actually. What we have is we want to calculate the acceleration, which is the change in the vector velocity divided by the time, which is V2 minus V1 vector over the change in the time. So we have an initial point and a final point. The velocity has changed directions, but it hasn't changed anything else, right? So in order to pull off V2 minus V1, this vector stays the same. This vector gets flipped around into minus V1. When we add these, it's like subtracting this. This is the resultant vector, V2 minus V1. But then we notice that this triangle, including the radii here, and the angle is similar to this triangle that we've drawn here with the angle in the center there. And because that, we can draw a relationship. We can say that this side of the triangle divided by this side of this triangle is the same as this side of the triangle divided by this side of the triangle, delta S over R. Okay, then we solve for delta V. We multiply over here and we have delta S over R times V1. And then we say that the acceleration is delta V, the change in velocity, divided by time. We just found what delta V is, so we take this thing and divide by time, so this is the new expression. Now we have to shrink the 2 points together and make time go to 0 to get the instantaneous acceleration. So we take the limit as this time gets shrunk down, and we want to group these two terms together, the ones that change. So we put these two terms together and these two terms together because these are the only ones that change. The distance between the points and the time changes, the velocity of the particle and the radius doesn't change, so we can pull it out. And then we're left with this expression. But then we go back to our drawing and realize that the limit, as time gets close to 0, the change in the distance between the points divided by the time elapsed is just the velocity of the particle anyway, so it's another V1. So V1 squared over R, and then the velocities all around the circle are all the same, so we just call it V squared over R. So we've covered a tremendous amount. If there's one thing I want you to keep an eye on or remember in this picture, or in this lesson, it's this picture here. When you have something spinning around at a constant speed that is unchanging, there has to be an acceleration. Even though the speed is not changing in magnitude, it is changing in its direction. Because this velocity is a totally different vector than this one. There has to be something making this change happen. Just like to speed up, there has to be a force. To make this thing point from here to here, there has to be some force. That's me pulling on the rope as I fling the thing around. It manifests as what we call a centripetal acceleration because we're going to learn that forces and acceleration, they go hand in hand and they point in the same direction. But that's why there has to be a force tugging this thing to keep it from sailing in a straight line to make it go into this curved motion. So in general, acceleration and velocity do not have to be pointed in the same direction. If the velocity is changing direction, there's going to be some portion of acceleration kicked in a perpendicular direction to make the change happen. You can think of this as being a force that's literally pushing the velocity and making the path curved. I'd like you to watch this a few times. There's a lot of subtleties in here. And then when you feel like you understand, follow me on to the next lesson. We'll continue to solve problems. Learn anything at mathandscience.com.